So now we return to Anchorage, Alaska, at the pooping end. We have the pooping end in Anchorage, Alaska. And we are generating now the AMZ 10 by 12 matrix, a relative of the periodic table, producing the 118 elements with their atomic number and atomic, in some cases, atomic mass. But what we try to do here is to produce what we call the PEN configuration. P stands for proton, E for electron, and N neutron. The PEN configuration. Let's write it up here. The PEN, P-E-N, configuration, proton, electron, and neutron. Proton is usually equal to electron in numerical value in the atomic orbital shell, and neutron has its own value. The PEN's configuration. When we don't have spaces here, and we don't want to clutter the matrix, so we just have the proton and the electron, which are equal. So we just have the PE and we leave out the N. So the 6 here we will have now is promethium, PM. 6 to 1, promethium. 6 to 2 will be samarium, SM. And that will be 62 proton, 62 electron. 63 would be europium, EU. 63 proton, 63 electron. We are given the PE configuration, and we're leaving out the N for the moment. So we have the PEN and we have the PE. Proton equal electron, and the proton equal and the neutron. So 63, and then 6 to 4 would be gadolinium, GD, 6 to 5 terbium, TB, 6 to 6 dysprosium, DY, 6 to 7 ulmium, HO, 6 to 8, and this number here, when I say 68, is the number of protons and the number of electrons, which is equal to the number of electrons. So 68 is ulmium, 69 would be tulmium, TM, and 70 would be YB, terbium, 71 would be lithium, LU, 72, something is missing here because then we have, it's supposed to be ending with 72, which is easily divisible by 12. And so if it's going on to 73, then there's something missing. So we have promethium at 6 to 1, neodymium at 60, promethium at 6 to 1, 62 samarium, 63 europium, 6 to 4 gadolinium, 6 to 5 terbium, 66 dysprosium, 6 to 7 ulmium, 68, that's where the mistake is at, erbium, ER, let's have the erbium here. Erbium, 68. 69 now would be tulmium. $78 would be YB. $71 would be lithium, and 72 hafnium. So we just have a little bit of clustering here because of the mistake that was made, but you could easily detect an error because of the irregularity. You know that the end of the matrix is supposed to be divisible by 12, and we had it not divisible by 12, so we know that there was a mistake. and therefore we have this cluster in here. But this is erbium, ER, 68. Let's write the atomic number and proton here, 68. Erbium. Then we have 69, thulmium. Then we have 70, terbium. And then we have 71, luthium, and 72, hafnium. And so we move up to 7 here. At 73 we have tantalium Ta, 74 tungsten W, 75 rhenium Re, 76 osmium Os, 77 iridium Ir, 78 platinum Pt, and 79 gold Au. 80 mercury Hg, 81 thallium Tl, 82 lead Pb, 83 bismuth Bi, and 84 polonium Po, divisible by 12. And so we go up to the 8, and here we have now polonium 84, 85 would be astatine 18, 86 radon Rn, 87 francium Fr, 88 radium Ra, 89 actinium Ac, 90 thorium Th, 91 protactinium Pa, 92 uranium U, and for that we have a 238 and a 235 uranium. 93 will be neptunium Np, that will be 237, and 94 will be plutonium Pu, that will be 231, 95 will be americium Am, and 96 will be curium Cl. Okay, so we reached a 10 by 12, so we have 2 rows to go. So we have 9, and this is now 96. 97 would be berkelium Bk. 98 would be californium Cf. 98 means the number of protons equals the number of electrons, which is the Pe configuration. And the pen, the Newton, when we add a neutron, we have the pen configuration. But like I said, we don't want to cluster up this imagery at the moment, and so we're just having the PE configuration, which is the number that you hear in the audio background. California CF, 98, 98 proton, 98 electron. Einsteinium ES, 99, 99 proton, 99 electrons. 100 fermium Fe, 100 proton, 100 electron. PE configuration. 101 mendelevium Md, 101 proton, 101 electron. 102 nobelium No, 102 proton, 102 electrons. 103 lawrencium Lr, 104 rutherfordium Rf, 105 rubidium Vb, 106 seaborgium Sg, 107 borium Bh, and 108 acium Hs. And so we come to the last row, in this 10 by 12 matrix, specialized chemistry matrix, a relative of the periodic table. And here we have now 10. Oxygen is 108. 109 is the neutron MT. 110 downstream DS. 111 Rentgium RG. 112 copernicium or copperusium CN. 113 Naurium NH. 114 Flavorium FL. 115 Moscovium MC. 116 Livermorium LV. 117 Tennessine TS. 118 Organism OG. 119 Enium, and 120 by new BN. And so we have completed the specialized 10 by 12 matrix here, chemistry matrix, and let's at least drop in the neutrons, the Penn's configuration for the first 20 basic, so write it to the Penn config for at least for the first 20, which was back in the days just for the high school syllabus. The first 20 plus some other specialized elements. But the world has got more advanced, so I suppose now that they must have increased high school syllabus to probably 30 or 40 elements that they should know to reproduce mentally. Back in the 1970s, it was the first 20 for the high school syllabus. Like I said, even elementary, people are racking off the periodic table mentally, just like that. Anyway, the Penn's configuration for the first 20. So here we have hydrogen here as proton. We have 0 neutron, and deuterium H1, 1 neutron, and tritium 2 neutron. Respectively, that would be protein. So helium, number of neutrons in helium would be, let's write it here now, 2 basic configuration, Penn. And there are a lot of isotopes. We put helium with 223 and 224 and so on. We couldn't go back to 221 because that would put us with the configuration of hydrogen. So it's above. So this is plus. In terms of, the last one is the N configuration here, N, and this will be the P, and this will be the E. So we have lithium now, and the configuration Penn would be 3, 3, 4 for the most abundant. But like I said, there are isotopes. That would put us with lithium with plus or minus 4 here, probably 3, 4, and 5. But for the most abundant, I think it will be 4 for the Penn's configuration for the neutron. So 4 for the neutron. Beryllium, which will be the 4th. The Penn's configuration here would be bracket Penn 4, 4, 5, So 5 Newton for the most abundant and stable, but then you could have Be4 and Be6. Some of them are radioactive, I believe, just like lithium here. But this is for the basic pen configuration for the most abundant and stable, 445. And so boron, B, would have no 5, I believe 6 would be the most abundant and stable. But then again, you have boron 7 isotopes, boron 8 neutrons isotope, and I believe a boron 5 as well. But you could look it up. Well, when I put the last neutron magnitude here, it's mean the most abundant and stable isotope. And so we have boron, then the next would be carbon. And for carbon, you have a 6, 6, 6. I think 6 would be the most abundant one there. But you have carbon 7 and 8 and others. You have a lot of carbon isotopes here. But I think 6 would be, for the pen configuration, 666. Carbon, nitrogen, and you have 7, 7, 7. You also have nitrogen 8, nitrogen 9, isotope, let's see here. Pen's configuration, basic. Then you have oxygen, you have 8, 8, 8, and you have oxygen 9 as well, isotopes, and so on. Then you have fluorine, F, 9, 9, 10, and you have fluorine 10, fluorine 11, probably fluorine 12, but I think 10 is the most stable and abundant here. And so you have neon, writing in the pen's configuration here, neon, Ne, and for neon you have 10, 10, and 10, 11, and 12. This is an inert gas, and I think the most abundant and stable with either 10 or 11 here. But then you have isotope 10, 11, and 12. So neon, next one will be sodium, Na. And for sodium, we have 11, 11, and 12. Because the atomic weight of sodium would be 23. So 12 would be the most. You add the proton, 11, and that, making it 23. Because you have this and this, making the atomic weight 12. Most abundant and stable. Oxygen would be 8 and 8, 16. Sometimes 15.999 is given as a most precise thing for oxygen. So 12 would be magnesium. And you have 12, 12, 12. Atomic weight of magnesium is what? 24, 25. So I think you got a 13 here for magnesium as well. But if it's 24, then it will be 12. We're talking about most stable and abundant. So you could check up for the accuracy of that. 13 would be aluminum. And for aluminum here, we have 13, 13, and 14. And the atomic weight of aluminum is usually given as 27. So 14 is the most abundant isotope. And you have also other isotopes, probably 15, 16, and so on for aluminum, but 14 is the most abundant, making the stable isotope having atomic weight of 27. And 15 will be phosphorus, and that will be 15 proton, 15 electron, and 15, 16, 17, and onwards are for the isotopes there. I think 16 will be the most abundant and stable for phosphorus. But then again, you could check on that for me. Phosphorus, then we have sulfur, 16, 16, 16 and others. Atomic weight is usually given for, that's 32 for sulfur, so 16 is the most stable and abundant. And then we have 17 for chlorine. And chlorine is usually given as 17, 17, 18, because the atomic weight of chlorine is usually given us about 35.5. So this make 18 neutron be the most stable, if we're going to take chlorine atomic weight to be 35. So you have others, 19 and probably 17, the plus or minus there comes in. But you could check for the neutrons magnitude there for me. Chlorine, then next would be 18 argon. So that would be 18, 18 proton, 18 electron, and 18, 20, and 22 electrons there. And argon has a lot of isotopes, so plus or minus, I think like about 29 isotopes there. So I don't, it's a bit ironic, as argon is inert, so and if it's inert or noble, then there's not much reaction. So maybe all the reaction comes along with the numerous isotopes. Anyway, let's go on. Argon, 18, 19 will be potassium, K, and that will be 19, 19, and 20. 20 will be more stable here, as atomic weight of potassium is usually given us about 39. So it will be 20 neutrons and 19 protons. The pen configuration here, PEN. And 20, the last one in the first 20 here, will be calcium 20, 20, and 20 plus. So here we have the Pence configuration of the first 20 elements. Meaning protons, electrons, and neutrons. Pence configuration for the first 20 elements. Pen meaning proton, P, E for electron, and N for neutron. And sometimes we just have it for PE, proton and electron. Protons equal electrons in numerical value for neutral atom. Okay, so